Everyone. This is essentially our Monday lecture, which you probably will be watching on Tuesday. We're going to deal with calculating or finding what's called the arc length, and then after that, the curvature. And we're also going to be looking at essentially finding what are called the three basis vectors of motion. There's the unit tangent, which you have met, and then there's two new ones called the unit normal and the unit binormal. I'm going to break this video up into essentially 4 sections to make it easier for you to go and look at a particular topic without having to scan through the whole video to try and find it. So the first topic that we're going to look at is pretty straightforward one. It's finding arc length. Typically, we're talking about finding the arc length when you're given the equation for the space curve. So there are 4 homework questions that deal with this. Our first one is a version of question 1, and where you're given a space curve, and its equation is 9t, 3 cosine t, and 3 sine t. And we're being asked to find the length of the curve from t equals -4 to t equals +4. So before we get into actually doing this question and showing you how we calculate it, first thing I want to show you is kind of try to visualize what's essentially going on here. Well, if you plotted this shape, essentially what you would get is a helix going along the x-axis. So it would be a shape that looks something like that. And can we imagine that at t equals 4, it might be here, say -4, I should say, and at here, t equals 4. And we're basically trying to imagine what would be the distance that you would travel going around this spiral. So an arc length is, as its name implies, it's the length of an arc. So you've got a space curve starting here, and it travels to here, and you're trying to find the length of that bent curve. Now, at start, really the application of this involves us using essentially a formula. And the formula says that the arc length is essentially can be found by finding this integral. It's the integral from a to b, where this is the value of a at the start, and this is the value of b at the end, of the magnitude of the first derivative. Interesting. That the magnitude of the derivative integrated from a to b will tell you the length of this arc or any arc. So as long as you know what the space curve formula is, and you know a start and finish value of t, then you're good to go. Well, up here, the question that we've just started looking at, if you differentiate it, you get 9, you get -3 sine t, and you get 3 cosine t. And then you find the magnitude of this vector. Now, the magnitude of a vector is the square root of each component squared and added. Now, superficially, you might think this is not going to be easy because there are going to be sines and cosines, or at least sines and cosines squared. And trying to integrate something with those kind of terms inside a square root is typically not going to be pretty. But in this case, it is. 9 squared is 81. -3 when you square it gets you +9 sine squared. And the other guy gets you +9 cos squared. And yes, identities matter. I hope you recognize that sine squared plus cos squared is 1. So 9 sine squares plus 9 cos squares would get you 9. So what you're now going to have is 81 plus 9, which is simply just the square root of 90. So the magnitude of the first derivative of your space curve is equal to this number. And since this is a magnitude, it's always going to be a number. Now that number, or I should say, it's going to be a single value because it could have t's in it, is a scalar, right? It's not a vector answer, it's a scalar. So when you come up to find the arc length, you're essentially going to integrate from a to b the magnitude of the first derivative of the space curve. And then you populate it with the values that you calculated or were already told. You were told that it started at t is -44, and you've just calculated the magnitude of that guy. And at this point, it is Calc 2. It is simply just integrating things the way you would have done in Calculus 2. So this is a number, so when you integrate a number, find its antiderivative, you basically just stick a t at the end. And then you evaluate it at t equals -4 to t equals +4. And what do I get? I get the square root of 90 times 4, take away the square root of 90 times -4. That will get me 4 square root of 90s plus yet another 4 square root of 90s. And our answer ends up being just 80 square root of 90s. 8, I should say, square root of 90s. And then I probably at this point start thinking about style points. Yes, it is a square root of 90, but the square root of 90 can be written as 9 times 10. So you get 3 out of that and a root 10. So the better answer is 24 root 10. And we are now finished. So the original question was, to find the arc length of this curve from t equals -4 to 4. And we have calculated it as 24 root 10. And we're always going to be looking for exact values in these questions, unless you get a question that says to 2 decimal places, which I believe none of the ones in the homework are. So we're going to have to deal basically with how to find the integral of the magnitude of a derivative. Now that itself might seem like it's not that bad, but each question has got its own little unique algebra tricks in it. For instance, the one we just finished, the algebra trick was to realize that 9 sine squared t plus 9 cos squared t was actually 9. And this next question doesn't use that trick at all. Sometimes you have to do u-subs. Sometimes you have to factor it so it becomes a perfect square. Sometimes you have to do integration by parts. I mean, there are many things that could happen. Let's look at what this one has. Well, if you want to find its derivative, you get 8, you get 2t, and multiply, that gets you 1/4 t squared. Now you want to find the magnitude of it. And that's going to be the square root of 8 squared plus 2t squared plus 1/4 t squared squared. So the magnitude of the first derivative of our space curve is now 8 times 8 is 64 plus 4t squared plus 1/16 t to the 4. And in case you're wondering, no, you are not allowed to call the square root individually into these and call this 8, call this 2t, and call this 1/4 t squared. It'd be really nice if that was allowed, but it doesn't work, so you're not allowed to do it. But I cannot integrate that. If I tried, I'd be in real trouble if I left it the way it looks. There's got to be something that we can do. So if you ever see 3 terms inside the square root and it's an arc length question that they expect you to be able to solve, these 3 guys are going to be a perfect square. In other words, it's going to be something times the same thing. Now you're used to doing quadratics like t squared plus 6t plus 9. That would be a perfect square. When you have got 3 terms like this, put them in order, either in this case increasing pairs of t or decreasing pairs of t if you like. And since I know it has to be a perfect square, I'm going to assume that that's what we have. 64 gets you 8, because 8 times 8 is 64. And 1/16 t squared is going to get me 1/4 t squared. This guy here is the same as that guy there. Do you notice it's a perfect square? Now you'd have to trust me, but if you multiply this by itself, it ends up being this guy. And the trick is basically, I'm just telling you right now, it's kind of magic. Take the smallest guy and take its square root. If it's a number, great. Take this guy, the biggest power of t, take its square root, 1/4 because of 16, and t squared is, half the power. And that will get you the perfect square. And now the square root and the perfect square essentially cancel each other out. And now we have the magnitude of the first derivative in a format that's going to be pretty easy to get the arc length for. So the arc length is going to be the integral from a to b of the magnitude of the first derivative. And we now know it's going to be from 0 to 1 of 8 plus 1/4 t squared dt. And the power rule says 8t. If you add 1 to the power here, you get that, and divide by the new power, you get that. So there's our guys, evaluated at t equals 0, and finally at t equals 1. So we now put in t equals 1, and you get 8 plus a 12th. Take away a whole load of zeros. I know the answer could be as a mixed fraction 8 and 1/12, but we don't like mixed fractions. We want an exact value as an improper fraction. So we basically do 12/8 is 96, and 1 more makes 97. And our answer for the arc length in this question is 97/12. Now, if you look at that question and you compare it against what happened in the first one, do you see that the algebra is quite different? Here it was a trig identity that got us to a place where we could work. Here we have polynomials which tend to generate, if you see 3 polynomials, they tend to generate 3 guys, and these 3 guys will make a perfect square. So that's your goal, is to look at the starting function and find its derivative, and then simplify this guy. This guy must be as simple as possible, because this guy goes here. And if this guy is really ugly, you're not really going to get beyond integrating here, because you won't be able to. So let's look at here is the version of question 3. And the first guy you got was the square root of 2t. Second term is e to the t, and the third term is e to the negative t. When you differentiate it, this is basically a constant, so you get the square root of 2. This gets you e to the t, and this gets you e to negative t. You then find its magnitude, And that's going to be this guy squared plus this guy squared plus this guy squared. Now that guy's 2. That's e to the 2t. And this guy here is e to the negative 2t. Right, let's now do a version of question 3. And this one has a combination of basically a weird multiple, the square root of 2t, and then an exponential that looks like this. And we're being asked to evaluate it from t equals 0 to 1. In this particular question, we find the derivative. And that guy is just simply the square root of 2. Derivative of e to the t is e to the t. And the derivative of e to the negative t is e to the negative t times the negative 1. We can now get the magnitude of this vector. So it's this guy squared plus the middle term squared plus the third term squared. You put that package together, what do you get? Well, you get 2 plus e to the 2t plus e to the negative 2t. And we have 3 terms. And if we ever see 3 terms, we have to be aware that what we're looking at excuse me, I've lost my windows. There we go. That what we're looking at here is going to be a perfect square. Now, the last time we had a perfect square, it was this fella here, right? And it had all powers. This counts as a perfect square. Hi, John. I wasn't expecting company. Can you hear me? Can you hear me, John? I cannot hear you. Your mouth is moving, but nothing is happening. I don't know if it's me or if it is you. It's me? Okay. Well, that's good news, because if it's me, I should be able to figure it out. I'm going to finish this question, and then I'm going to go out and then in. So we rearrange the 3 terms. The square root of this guy is e to the t, and the square root of this guy is e to t, so there's a perfect square. To get the correct terms, you always have to put biggest power to least power. That's a big power, that's e to the 0, that's e to the negative 2. So when we put this package together, we now get this. So our arc length is going to be the integral from a to b of that guy. It's going to be an integral from 0 to 1 of this guy. And it's going to be e to the t, take away e to negative t, evaluated at 0 and at 1. So we're going to get e to the 1, e to the negative 1, take away e to the 0, take away e to the 0. That's e to negative 1. 1 take away 1 is 0, and there is our answer. Okay, I'm going to go out and in and see if I can fix John's problem. Was the first one. We're going to be looking at how do you find the arc length of a given curve. And so the formula for doing it is essentially the integral of the magnitude of the first derivative. Now we only have one more example of that because there are only 4 questions. So I'm going to use that one just to give you a kind of very quick update on what's going to happen. So in the first 4 questions, these would be considered the more straightforward ones. You're going to be given the space curve, at least the equation of the space curve. And you're going to be asked to find the length of the curve from 0 to 1. So if you can imagine, and this is me just pretending I know what the space curve looks like, but if you can imagine that t equals 0, the curve is here, and then it does something like that, and then up here, it's t equals 1. When you're finding the arc length, you're basically finding the distance you would travel if you went along the curve from t equals 0 to t equals 1. So what we're going to do now is go through the process. The formula for calculating the arc length is it's the integral, calc2 integrals, from a to b, where the start value of a, the start value of t is a, and the finish value is b, of the magnitude of the first derivative. And most of the problem that, you know, is going to be an algebra issue is to be able to integrate something. The form of this has to be as simple as possible. Integration is not easy, especially when you find out that all these questions end up having square roots in them. It's going to be really hard to do an integral with the square root. And so we typically are given questions, because they're doable, that this piece here can be simplified. So let's see what we have here. Our original function is 8t squared t cubed. If you differentiate this, that guy gets you 0. This guy gets you 2. And this guy gets you 3t squared. So far, so good. Now what's going to happen is we're going to find the magnitude of this guy. And that's going to be the square root of this guy squared plus the middle guy squared plus the end guy squared. And in this question, that ends up being 4t squared plus 9t to the 4th. Now, the most likely thing that's going to happen, you know, this ugly guy in the square root, the most likely things that are going to happen is that it ends up being a number, which is the question 1 that I did that you haven't seen, but you can watch the video. The second thing that can happen is that the terms, these terms here, end up being a perfect square. You know, like x squared plus 6x plus 9 turns out x plus 3. And a perfect square is really nice. So if you factor it, you get a perfect square. And the square root and the perfect square cancel out. And the last possibility is this one. So if I just rewrite the first derivative, it's the square root of 4t squared plus 9t to the 4th. And I'll just emphasize this again. You are not allowed to take square roots and do them separately. So I can't pretend that that's 2t plus 3t squared. That doesn't work. We can't do it. What I can, however, do is I can pull out a t squared as a common factor. And when two things are multiplied inside the square root, You are then allowed to do each one separately. And the square root of t squared is going to be t. So what I have here is the best version of the magnitude of that guy. It might not look great, but it's the best I can do, and it will work. So to get the arc length, it is going to be the integral from a to b, which is from here to here. The magnitude of this guy, dt. And that's going to be the integral from 0 to 1 of the magnitude of the first derivative, which ends up being this guy. Okay, harking back to what you did in Calc 2, if someone asked you to integrate a function that looked like this, the most likely strategy would be integration by parts or a u-sub. One of those works and the other doesn't. So looking at this integral, so it's essentially a Calc 2 question. What would be the u-sub that you should use to make it work? Because I said only one of them works and it's a u-sub. What is the u-sub you should use in this question?
Well, I think u should equal 4 plus 9t squared, and then derivative of that is just going to be 2t, but you have one left over already. So
Okay, sounds like a plan. So 4 plus 9t squared is our u-sub. If I differentiate it with respect to t, that gets me nothing, and I get 18t. If I then do the crossover, I get 18t dt, and then if I divide both sides by 18t, I can isolate the dt. So this integral, I don't put the limits of integration in, becomes t, the square root of u. The dt gets replaced by 1 over 18t du. The t's cancel, which is exactly what we'd expect, the t's to disappear. And we now have 1/18th the square root of u du. So the original integral looked like this and really wasn't doable. And with the substitution, I've now converted it into this. Of course, if you want to integrate a square root, you're going to have to call it a half power. You're then going to add 1 to the power and then divide by the new power. Well, dividing by 3/2 is the same as multiplying by 2/3. So if you take this fraction and you multiply it by 2/3, you get 1/27th, I believe. And then I'm going to convert it back into the original variable, which is that guy. And at this point, then we can put in the limits of integration, which are t equals 0 to t equals 1. So continuing with that, the arc length. If you plug in 1 into this, you get 1 over 27. 4 plus 9 times 1 squared is still 9, to the power of 3/2. Take away 1/27, 4 plus nothing, which is what? 4, to the power of 3/2. So that's 1/27. Well, let's pull it out as a common factor. 13 to the 3/2, take away 4 to the 3/2. So far, so good. Right, now we've got to do style points. The original question was, we would expect square roots. You know, it's here and here, it's all over the place. So 13 3 to the halves is the same thing as 13 square root of 13. And this guy is the same thing as 4 square root of 4. It's like 1.5 powers, right? So you get the number and then you get a half power, which is a square root. So 1.5, 1.5, 1.5, 1.5. So far, so good. Do you notice that the square root of 4 is actually 2? And so the last piece could be simplified as 4 times 2, which is 8. And that guy is your arc line.